Okay, so yesterday we talked about weak acids, and today this video is going to be over weak bases. They're very, very similar in the way that generally the setups are. The only thing is going to be different is that instead of A, we're going to use a B for our base, and then remember that a base is going to accept a hydrogen, and that's going to give us hydroxide. So you have your K expression, here's your KB expression. So for example, with this reaction, and remember, don't include water, our KB expression is going to be, again, products over reactants. Don't forget those charges. Okay, no water included. Now, there is a relationship between Ka and Kb that is numerical. So with Ka and Kb, if we multiply our Ka times our Kb, we're going to get our Kw. Okay, and this is only works for our conjugate acid base pair. So you can't just have a Ka from one acid and a Kb from a different base. So if they're conjugate acid base pairs, when you multiply them together, they will give you your Kw. Don't forget pKa and pKb is just the negative log, and then if we take our pKa plus our pKb, that's going to equal 14, just like our pH plus pOH equals 14. Right, so let's take a look at an example. So you'll notice this is very similar to our examples that we did for our acids. The only difference is that we are now solving for our hydroxide ion concentration, because this is a base instead of our hydronium. So if it's asking for pH, make sure you're noting, oh, I'm solving for hydroxide ion, so I'm going to have to somehow convert. There's multiple ways to do it, from our OH concentration to our H concentration, or you can find your pOH and then find pH, either one. Okay. All right, so set up your isotable table just like how we've been doing it. So we have our 0.5 molarity here, 0, 0, and then negative x plus x plus x. Plug it into our Kb expression. We know our pH is 12.16, so we can find our pOH just by subtracting from 14. And then that will give us our hydroxide ion concentration. And once we have our hydroxide ion concentration at equilibrium, that is our X value. Okay. Now, when we look at this, what's in our beaker here, we're going to have, because again, this is a weak acid, we're still going to have some of our initial methylamine, which is our weak base. We're going to have some of its conjugate acid, and also some hydroxide floating around in here as well. All right, once we find our X value, again, all we're going to do is start solving things. So once we find X, we can plug it into our Kb expression, solve for our Kb value. And then for percent ionization for a base, we're looking at hydroxide ion concentration over our concentration of our base, and then times 100. So very similar to ionization with a acid. Again, we're just looking at hydroxide instead of hydrogen ion. All right. So pause the video now and work on your second example, or example 4 in this case, and then you can start the video again and check your answers. All right, so first thing you want to do is in H3, write our equilibrium expression so we can do our ice table. Okay. We initially have a concentration of 0.500, remember no water, minus X. And our Kb expression and plug in our X value, so it's going to be X squared over 0.500 minus X. Okay. Our other value they give us in here is our ionization value. So from this, we can solve for our hydroxide ion concentration at equilibrium. So we know that our percent ionization is equal to hydroxide ion concentration over our ammonia concentration times 100. So we're just going to set that equal to our 0.598. This is going to be equal to x over 0.5 times 100. And then you can solve for x, and you end up with 2.99 times 10 to the negative third. And I'm going to double check that and make sure that math is correct. Not that I don't doubt Miss Baker, but just want to double check. Okay, so that's our x value. So now that we have our x value, we can solve for our concentration of our other substances at equilibrium. Okay, so our concentration of NH3 is going to be 0.500 minus x. Our concentration of OH is going to be equal to our concentration of our hydronium ion, and we've already solved for that because we solved for x. So now we can plug our values in to our Kb expression. So 2.99 times 10 to the negative 3 squared. And when you do the math, should get, hold on, let's see, 1.0 times 10 to the negative fifth, and there is our Kb value. All right, and then the next question asks, what is our pH at equilibrium? Okay, so we're looking for pH as well. So since we have our hydroxide concentration, we can find our pOH pretty easily. So that's negative log 2.99 times 10 to the negative 3. I'm going to box this. So we get 2.52, and then we just need to take 14 minus 2.52, 11.5, and that is our pH. Now, when you're doing these types of problems, make sure that you're checking back and thinking, okay, does this make sense? A lot of times too, with these types of problems, especially if it's a multiple choice, be looking at answers that are like completely off base. We know that this is a weak base, so our pH has to be greater than 7. If you have a pH answer that's less than 7, that's acidic. You can cross that answer out because we know it's going to be greater than 7. Okay, so just make sure that you're looking back through and thinking logically, okay, what would my possible answer be? As to what's in the beaker, so we're going to have some ammonia, ammonium ions, and hydroxide ions floating around in our beaker. All right. And there are weak bases.